Today we're going to be looking at predictions. Something we should have added on the day one notes. We'll throw it in here real quick. Oops, that's a pretty bad star. That's supposed to be a star. It's because I'm hangry and my fingers are not going to work right. R, our correlation. Is unitless. And I've seen more than a few problems that ask that question in previous curriculums and tests and stuff like that. R is unitless. Okay, regression line. The regression line is where we make our predictions, and it is in the form of y hat. You haven't seen this symbol yet. Y hat equals a plus bx, where a is the y-intercept, b is the slope, and y hat is the predicted outcome of an input. Y hat, that's a pretty bad hat there. Of a given input from the line of regression. The line of regression. I gotta fix that hat. That's pretty, that looks like an AY hat. So technically, when you go into your line reg A plus BX and you do your calculation, and at the very top, it's telling you what the form of the line is right here. This technically should be Y hat. My guess is that they aren't able to program a little something over that Y in the calculator itself, but that should technically be Y hat. Okay, that's a predicted value. Okay. So if I have a graph, a scatter plot of some sort, I'm going to make a scatter plot with a few points here, kind of scattered, positive correlation, and let's say I've got a line of regression here that does something maybe like this. Okay. What the y hat is if I pick some value of x, let's say this value of x, whatever it is, and I use it to predict, I want to predict a value of y. What I do is I come up to the line of regression, I'll make a turn, and I come over here and read how high I am on the y-axis. This would be your y hat value. So for this value of x, this is the predicted outcome. Now that doesn't mean that there's a point there. It just means that this is our best guess at what a point would be if it were there. Does that make sense? And sometimes you'll find that the points are above and below this line of regression. That's okay. This is our predicted value. you want to make sure, and I'll cover this in a little bit more detail later, you want to make sure you're predicting within a reasonable range, because this line may not continue to be linear forever. In fact, it probably doesn't. So even if you think about the exponential growth of a population where it starts out slow and then it curves up, eventually that's going to top off, maybe even go down, right? You can't have continual growth generally in a real life situation. And what that gets at is extrapolation. I'm okay making some values, some estimates from these inputs that are within the range of my data, but if I try to step outside of the range of the data, we end up with an extrapolation problem, perhaps. This is when we predict. Outside of the range of the explanatory variable. We run the risk of an extrapolation error. Let me give you a scenario on that. Any baseball fans in here? Couple? Good. I'm not really a baseball fan. I don't follow any particular team or anything like that, but I will tell you, if you get an opportunity to go see a professional baseball game, even if you don't like baseball, take it. It's unbelievable how fast that ball moves and how quickly those guys react to it. It's quite interesting. I find baseball interesting almost more on a historical level than anything else. In the late 90s, there was a home run battle between two players. Anybody know who they were? Two guys. There was Sammy Sosa and a guy named, what's that? Oh gosh, it left me. I had it in the last class. Sammy Sosa and Mark McGwire. And these two guys specifically were hitting home runs and home runs and home runs, and they were going after the record. And I can't remember who set the record, whether it was who it was originally back in the day, but they were going after this record, and for a number of years they kept sort of beating the record. And I think in the last year that they were going for that record, they tied, if I remember right. I want to say it was like 62 home runs or 72 home runs in a year. I forget now. It's not really important, but it was more than anybody else had ever done. And it was big news. I mean, even the people who weren't really into baseball, it got a lot of attention for the sport. So I'm going to presume that if we graphed the highest number of home runs in any given year in the 1990s, that would be a somewhat linear graph going up and up because of these two guys. Okay, so it's somewhat linear and it's increasing. In the early 2000s, that all came crashing down. And here's why. They discovered that those two, and probably many others, were doping. There was they were using performance-enhancing drugs, and so the league put the kibosh on that. They did, I think, from what I understand, being an outsider, they did a really good job of controlling the performance-enhancing drugs. And so what's happened is, if you had used a graph like that to predict into the 1990s, you'd probably be fine. But if you wanted to know how many home runs you thought they'd do in 2005, you'd have been sorely mistaken, because that number dropped off significantly, and I haven't heard of anybody even coming close to it since. Now again, I don't have my ear to the ground on that, but you couldn't miss it at this time of existence. Those guys were on the news all the time. It was, you know, oh yeah, and along with the weather, Sammy Sosa hit another 3 home runs this week. You know, it was nuts. So anyway, extrapolation is when you're trying to take some data and look farther out or back into than what you actually, the range of the data itself. So watch out for extrapolation. We still do it. It just, you need to make sure that whoever is paying attention or reading your work understands that you're concerned about that. Okay, residuals. Residuals, it's an easy calculation. They are the difference between the actual value of y for an individual, a data point, and the predicted value of y hat. So literally, the formula is just y minus y hat. If your residual is positive, it means that your data point lies above the line of regression. If your residual is negative, it means it lies below the line of regression. And we need to talk about another way of calling the line of regression something. LS, LR. This stands for least squares line of regression, and it's just something you need to know about. Now, I've talked about the line of regression, but what I'm really talking about is the least squares line of regression. And you'll hear this called a number of different ways. Line of regression, sometimes we informally call it line of best fit, but that's probably not very statsy. Least squares line, if you see something called least squares line, know that it's just the line of regression. And what they're talking about is this. I'm not going to give you the calculation because I'd have to look it up myself, but if we have some line of regression, and we'll keep it simple, let's say I have some points on this side of the line of regression and some points on this side of the line of regression. How the line of regression is calculated is this. The smallest distance, vertical distance from the points below and the points above is turned into an area by making, the calculator does this, it essentially makes, not essentially, it does, it makes a box, a square out of each of these data points. And so our original points and our original distances go into making these squares. And the area of the squares below the line would equal the area of the squares above the line. That's how the line is calculated, how it's placed. Now, why they use a geometric model for that, I'm not entirely sure, but I'm also not going to concern myself with that because I don't want to go change the world. I'm just telling you how it's done, and the calculator does it, and we're happy with that for the most part, okay? But you do need to know sort of what's going on here. When they say least squares line of regression, they're not talking about anything different. It's just the line of regression, or the line of best fit, or the least squares line. It's just line of regression. It's just different ways of saying it. But the area of the boxes below the line equals the area of the boxes above. So when I say least squares line, you're thinking line of regression. It's the same thing. Okay. All right, we're almost done. I want to go back and look at the equation that we have for the Archaeopteryx data that we put in the calculator a little earlier. Let me get that calculation back up here real quick. So if I were to draw this situation, we have femur length and humerus. So this is the Archaeopteryx. And again, I don't think it's actually in your notes, but I have an issue here. I think that we should petition the English department and all English departments to no longer allow words with 3 vowels in a row. I mean, that's just craziness in my opinion. I think that can be done with less letters. If I were to draw this out, it would look something like this. Femur, humerus, and my line of best fit, my line of regression, my least squares line is doing something like this, and I've got some data that's pretty close to the line. I don't know, something along those lines. That's probably not exactly right, but that's okay. And my equation for the line, y hat, equals negative 3.7 about, that's my number there, my A, plus 1.2x. Now, if we want to predict some values of an Archaeopteryx humerus, what happens if I put 0 into this equation? How long is the humerus if the femur is 0? It's not, though. Mathematically, it's negative 3.7. That's what the y-intercept says, right? But that doesn't make sense, right? You can't have a negative length. Actually, no measurement can be like negative. No linear measurement can be negative, right? So you can't measure the arm length to be a negative value when a femur is 0. So the thing that I'm saying about this, or where I'm trying to go with this, is the y-intercept values are oftentimes nonsense. They mean nothing of any consequence at all. And this is a great example of that, because when the femur is 0, I got negative 3.7 centimeters of humerus. It's not possible. So what ends up happening is these values, you know, just shy of below this and just shy of above our range, that's where we start looking at that extrapolation. So in reality, this line is only linear within this range of the data. After that, this line's going to do something probably like this and go from 0, 0, right? If you have 0 femur, you've got 0 humerus, right? It's only linear within that range. Make sense? Okay, so anyhow, you can predict within here. You're okay. You can predict within there. If you step outside of it very far, you need to mention, I gotta maybe